Hey Kipsters, today we're working in the final lesson of Module 4, Lesson 29, Word Problems. Take 15 seconds to make sure your paper looks like mine. And let's get started. So our objective today is that you'll be able to write word problems into systems of linear equations. So we know we're going to be using system notation, and then we're going to solve those system of equations using elimination and the substitution methods. So let's look at example number 1. Example number 1 says the sum of two numbers is 361 and the difference between the two numbers is 173. What are the two numbers? What do we need to do first? We need to define our variables. If we define our variables, we can better represent the situation we have been given. What should the variables be for this problem? Let x represent one number and let y represent the other number. Well, I know that I'm going to use system notation, and lucky for me, everything that I pulled out is exactly what I want to use to build up. So my system looks like this. All right, which method have we learned is going to be most useful to eliminate my y term? Yeah, I'm going to use the elimination method. So I see when I'm adding the like terms vertically, my y terms cancel out. And I get that x is equal to 267. All right, so remember, I want to use x to substitute into either one of my given linear equations to then solve for a y. So by default, I'm just going to pull out my first equation, and it's x plus y equals 361. And I'm going to substitute 267 for everywhere I see an x. 361 minus 267 gives me a y of 94. So that means my solution set to this problem is 267x and 94y. And the answer to the question, what are the two numbers? Okay, so we said that x was the first number. So the first number is 267, and the second number is 94. It's kind of cool how we can use linear systems to answer questions like this. All right, let's get a little more complex. Example number 2 says there are 356 8th grade students at Euclid's Middle School. 34 more than 4 times the number of girls is equal to half the number of boys. How many boys are in the 8th grade at Euclid's Middle School? How many girls? Go ahead and use cubes to annotate your problem. Let's define our variables. What are we talking about in this problem specifically? We're talking about the total number of 8th grade students, and the categories that we're broken down into are the girls and the boys. So let's define our variables and say let x be the girls and let y be the boys. All right, and we know we're building a linear system of equations, and the first sentence may be helpful. It says there are 356 8th grade students at Euclid's Middle School. All right, so I know that the middle school is made up of girls and boys, and that total is 356 kiddos. All right, now it says that 34 more than 4 times the number of girls. All right, I said the number of girls is going to be represented by the variable x is equal to half the number of boys. All right, remember when we attach variables and fractions together, we're showing multiplication. So I can pull that together to say that for x plus 34 equals 1/2 y. We know several methods for solving systems of linear equations. Which method do you think will be the most efficient and why? Honestly, there isn't a most efficient method. What I think would be the most useful to model is actually how to go ahead and eliminate the fraction from this 1.5 y. So let's pull out the second equation. And if we want to eliminate this fraction, what do we need to multiply both sides of the equation by? The denominator. So I'm going to multiply my right side by 2, and I'm going to multiply my left side by 2. And I know that the left side of my equation is going to be transformed into 8x plus 68 equals y, because over here on this right hand side 1/2 times 2 is going to cancel out. So now I'm going to rewrite my system of linear equations to capture what I have now transformed my equation into. So it's x plus y equals 356. I didn't touch the original equation. And then the second equation is now 8x plus 68 equals y. Now, because I have one of my equations in terms of y, it's actually going to be easy for me to use the method of substitution to begin to solve for the solution. So I'm going to rewrite the first equation like I've been given. And the second time when I rewrite it, I am going to account for y now equaling 8x plus 68. And that's all equal to 356. So I have some like terms that I can add when my parentheses drop off. 8x plus x is 9x now, plus 68 equal to 356. All right, let's talk about what y equals. All right, so we know that x equals 32. We're going to take 32 and we're going to substitute it into either one of our given equations. What this means is that the solution set for this system of linear equations is 32 and 324. But remember, we're working out a word problem. So what does this mean? What does the solution mean in context? Well, since we let x represent the number of girls and we let y represent the number of boys, it means that there are 32 girls and 324 boys. How can we be sure that we're correct? Well, when we substitute the values into both of the equations of the system, we can see that it makes the equation a true statement. And let's take a look at that. When I substitute 32 plus 324 into the first equation, I get 356 on the left equal to 356 on the right. So I know that that is true. And likewise, in the second equation, when I substitute 32 for x and 324 for y, on the left, 128 plus 34 is 162. On the right, half of 324 is 162. So I know that 32 and 324 is the solution for the system of equations. We're doing good, y'all. Let's look at example number 3. A family member has some $5 bills and $1 bills in her wallet. Altogether, she has a total of $62 bills. How many of each bill does she have? Let's let X represent our number of $5 bills. And let Y represent the number of $1 bills. All right, so defining our variables is going to help us be defining our variables helps us to better represent this problem. Now that we know that X is the number of $5 bills and Y is the number of $1 bills, what do we need to do? We need to write the equations to represent the information in the word problem. Using X and Y, write the equations to represent the information we are provided. It says, altogether, she has 18 bills, a total of $62. This must be represented with two equations. The first equation is going to be x plus y equals 18 because it says all together she has 18 bills. All right, and the second equation is actually going to be the amount of each bill that she has. Two equations that represent this problem. What is it called when we have more than one linear equation for a problem, and how is it represented symbolically? We have a system of linear equations. We know several methods for solving systems of linear equations. Which method do you think will be the most efficient and why? You could use either of the methods that we've used. The elimination, for purposes of this example, I'm going to use the elimination method. So it would be easy for me to eliminate my y terms if one of my y terms was negative. How could I make one of my equations negative? I could multiply my left and my right side by -1. So I'm going to take my first equation. I'm going to multiply my left and my right side by -1. And that transforms the equation. It's going to take the opposite of every term. I'm about to rewrite that so we can see that better. So the new system of linear equations I'm evaluating is -x minus y equals -18 and 5x plus y equals 62. Notice I dropped off that one y. You know that that's $1 bill. All right, so now I can easily eliminate my y term when I add these linear equations. And I get that x is equal to 11. Remember, we always use our x to substitute into either equation. And I'm just going to use the second equation. I get 62 minus 55 with a y of 7. What that means is the solution set is 11 and 7. In the context of this problem, because we let x represent the number of $5 bills and we let y represent the number of $1 bills, it means the family member has 11 $5 bills and 7 $1 bills. The next step is to check our work. It's obvious that 11 plus 7 is 18, so we know that the family member has 18 bills. It makes sense to check our work against the actual value of those $18 bills in this case. So let's check the second equation. When I substitute in my x of 11 and my y of 7, on my left side I get that 55 plus 7 does indeed give me 62. So because my left side equals my right side, I know that 11 and 7 is the solution to this equation. All right, example 4. Again, we're going to work together to solve the following word problem. A friend bought 2 boxes of pencils and 8 notebooks for school, and it cost him $11. He went back to the store the same day to buy the school supplies for his younger brother. He spent $11.25 on 3 boxes of pencils and 5 notebooks. How much would 7 notebooks cost? Well, what do we do first? First, we need to define our variables. If we define our variables, we can better represent the situation we've been given. What should the variables be for this problem? We know that we need to represent the information in the word problem, so we're going to use x and y to write these equations. I'm creating 2 equations that represent this word problem. When I have more than one linear equation for the problem, how is that represented symbolically? What's that called? It's called a system of linear equations. So the first sentence says, a friend bought 2 boxes of pencils and 8 notebooks. Well, if I'm buying 2 boxes of pencils, that's going to be represented by 2x, and 8 notebooks will be represented by 8y. And it says I spent a total, it cost me $11. Representing the second equation, it says I spent $11.25 on 3 boxes of pencils. Again, I'm going to attach a 3 to the variable x because that represents the cost of a box. And 5 notebooks. Attach 5 to the variable y. We know several methods to solve systems of linear equations. Which method do you think is going to be the most efficient and why? You can solve with either of the methods we've been given. What I'm actually going to do is transform the equation by multiplying both equations by 3 and 2. So I'm going to pull out the first equation, 2x plus 8y equals 11. And I want to multiply both my left side and my right side by 3. That's going to transform my new equation into 6x plus 24y equals 33. Alright, working the same way with my second equation. I'm going to pull that one out. That's 3x plus 5y equals 11 and a half. I'm multiplying it by 2 because when I multiply the top equation by 3 and the bottom equation by 2, I create an x term of 6. I could go a step further and multiply by -2, then I'm going to create an x term of -6, and then I can eliminate my x's. So when I multiply each term by -2, I end up with -6x -6x minus 10y equals 11 and 2500ths times -2. 11 and 2500ths times -2. Get -22 and a half. All right, now let's go back and stack my equations to see how I'm comparing. I am looking at, now that I've done some work to transform both of my linear equations, I can rewrite the system I'm looking at. I'm comparing 6x plus 24y equals 33 and a -6x minus 10y equals a -22 and a half. It's obvious now I should use the elimination method. Just 3/4. Y is 3/4. All right, what do I do with y? I'm going to use 3/4 to substitute back into the equation. I'm going to go with my first equation, and I pull it out. 2x plus 8y equals 11. I'm going to substitute my y for 3/4 equal to all right, now divide both sides by 2. I get that x is equal to 5 divided by 2. What does that mean in the context of my problem? I'm sorry, so x is equal to 5 and a half. All right, so what does that mean in the context of my problem? My solution set is decimals 2.5 and 7500ths. In the context of this problem, that means that 7 notebooks would cost 75 cents each. So 7 times 75 cents would cost me $7.25 for 7 notebooks.